Hi everyone, welcome to another episode of Triboelectric Tuesdays where we dive into the technique of separating botanical trichomes from biomass. If you're interested in this topic, keep watching. So when we make a product, we're continuously improving it. And what I want to talk about today is the lessons learned so far with the Plasmastatic Trichome Separator. We are currently at version 3. If you place an order today, you would get a version 1.4. And of course, it's just our continuous improvement process. And so whatever we learn gets applied to the following versions. And we don't make huge production runs. So our products are constantly improving. I think that's what makes us different from other people. And so what I want to talk about today is what are those lessons learned and how they were employed into the new device. The biggest challenge of triboelectrically charging particles to get the process to work well is a balance of the circulating load. And what do I mean with circulating load? Just think about it, right? The load, the particles that are loaded onto the system going around in the circle. That's a term actually from mining. That's where I learned it from. But in this context, what I mean is that when you put biomass into the device, not all of it separates in one go. So it has to go around a second time. And so the issue with the circulating load is that if there isn't enough particles inside the system, the particles don't interact. There isn't enough friction and they don't charge. And so the magic doesn't seem to happen. If you have too many particles, then the system gets overloaded and just the particles don't charge. And when they come to the separation chamber, they flood the system and they don't separate. So there's like a sweet spot, right? That's the point. So to get that sweet spot is a balance of geometry, distance, pressure, etc. And so the biggest challenge that I've seen is particles settling on the tube. What happens is that if there's any kind of dead zone on the device, particles will settle. And so what we found was that if we did a spiral tube, if we fed the particles from the top to bottom, it creates a lot more dead zones. And so there's a lower pressure gradient in certain areas of the tube. And so anyways, when you're feeding from the top to bottom, it's more likely that particles will settle. And so you're going to have accumulation of particles in the tube. And of course, we don't want that. So you're kind of forced to, spiral upwards. And that does a really good job of getting the particles to lift up. And so there's like a very fine line on the tube length and the pressure and the design and everything to get the particles to settle. If the tube is very big, you need a lot more air to go through the system. If the tube is very small, you need less air, but then you can only put a smaller amount of bio through it. So you have a settling problem in the tube, which is one of the concerns that we've had in the first few versions. To reach that expectation, we have to be within certain design limits, and we have to take in the design specifications from all of the manufacturers involved. Like, for example, there's a suction feeder. So the suction feeder has a minimum pressure where it can work under for it to be efficient. But then the pipes, too, they have their specific, the tubes, they have their specific conditions. So anyways, you put in more air, and that solves the particle settling in the tube, right? Okay, cool. But then that creates further problems downstream because the more air you put in, here we're just talking about volume. But see, what happens is that when the air comes out, it goes into a diffuser. And so the diffuser is designed with a specific amount of airflow. And so when you increase the airflow, particles that come out of the diffuser go a lot faster. And so then the terminal velocity of the particle has now increased because you're artificially like shooting it out of the gun instead of just falling by gravity, which is what we intended. So as a particle comes out of the diffuser, if the particle is traveling too fast, then that just makes it really hard for the attraction that you have from the electrodes separating particles, right? So then you need to change the design of the diffuser. Just by adding more air, then you need to change the design of the diffuser. Okay, cool. Then if you change the design of the diffuser and you're putting more air into the system, now you need to deal with more air within the system. And because you're putting more air, you're likely also putting more particles. So then you need to exhaust this air somehow, right? So if you can follow me through this, you can really see that we're fixing a particle settling on the tube, but we fix it by increasing airflow. And then that means that we have to change the diffuser. And then that means we have to do something about the exhaust. So that's kind of like my point on how all of these things are correlated, and it's just like a barrage of things. So anyways, basically the first step was to find a sweet spot for the air pressure or the airflow that we need to prevent particle settling. And so surprisingly, it was about double the airflow that we originally designed the system for. And of course, this created all sorts of havoc. So the first thing that we had to redesign was the diffuser, right? Because the diffuser was designed for the original airflow, which is now doubled. Without giving too much of trade secrets, so here is the computational fluid dynamics of this process, of the design process of the diffuser. And so basically what we do is we just model using computational fluid dynamics how the particles would travel through the diffuser and how they would behave. Every time you model a process, you get a lot of data, right? How the particles flow in theory, right? And so because we also have real world information on how particles actually flow in real life, we can have a pretty close idea if what the computer is saying is accurate or not. And so every time you do a model, that teaches you something. And so you take that information and you make an improvement and you create another model. And so through this design process, using CFD, we were able to take a diffuser and double the amount of air we could put through it and actually reduce the velocity of the particles coming out. So we doubled the airflow, but we also reduced the particle velocity. The slower particle velocity makes the separation of the particles more effective, more efficient. You get a better separation and you can separate more because as the particle is falling, it takes a lot longer time for it to fall, and it's more likely that it will actually gather on one of the plates. Yeah, so that process is really cool, right? Where using computer simulations, you can really dive down into making something that is just extremely functional. And so I think that is the biggest breakthrough that we have in just the design of this diffuser, the state diffuser, that really is a lot better than the first 20 iterations that we have at this point. Can't stress how significant that is, because just the flow pattern in the videos that you guys are going to see, the particles are not like jetting out anymore. And unfortunately, we kind of lost the money shot where the first iterations, the particles were just like basically shoot horizontally because they were traveling so fast and the attraction was so strong. But now, because the particles are traveling so slow and the traction hasn't changed, this money shot no longer is there, which is kind of a shame, but it is what it is. So of course we fix one thing, but break another one. So there's other things that need to be fixed. And so what happens when you have double the amount of air flow coming into this thing? All the downstream processes are not designed to handle that material. So now there's set currents of air that form all sorts of vortices inside the device. And so when you're working with such a fine powdered biomass, there's going to be dust everywhere. It's kind of the nature of the beast, but this does increase that and it makes it a little bit more complex. So we did a lot of simulations to understand how air actually flows within the system. You can't really see it because it's air, right? So you don't really see it. You can understand how the air flows, but you can definitely simulate it, and that's where simulation really comes in handy because you can really see how particles travel. And then we found out some of the issues that we were having as far as like how air was traveling throughout the system and the problems that was causing. That's where computational fluid dynamics really comes into place, and you can really see things that just were not obvious from just analyzing it, right? You could take a look at these CFDs, renderings. I'm gonna really understand how the air is moving within the system right now. And that's a problem because the very light particles that don't have any cannabinoids and probably won't separate anyways, those are the ones that are going straight out through the exhaust. And so even though the exhaust can handle it, you're pulling up these air particles because you have like these jets of air going up, right? And so it just brings along all the fines with it. And so an obvious next step was, hey, what do we do to break up these vortices that are, carrying particles along with it? So yeah, of course, we had to have another type of diffuser that would break up the vortices and just disrupt the airflow, right? So it wouldn't carry stuff up with it. And yeah, this is another one that was just wild. The kind of ideas that were proposed were all sorts of cyclones and just real crazy stuff that, when you're designing this stuff, you have to think about it. How easy it is to clean, how easy it is to manufacture, what is the cost implication? And this stuff just goes crazy. So at the end, we ended up with a simple diffuser that it's basically a whole bunch of holes, kind of like what a muffler has going on, sort of similar, that just disrupts that air current. And it really is effective at, removing somewhere 60 to 90% of those fines, making it out. But more importantly, just the velocity of the air exhausting the system is greatly reduced. And so that's a huge win without significant redesign or costly parts or anything like that. And it's something that can be carried over to other versions. Yes, I think the diffuser really disrupts the vortices, and that fixes that issue. The other issue that we ran into is it's just when there's a lot of particulate, of course, the fines become a problem. So the SOP, dialing in the SOP really helps. So what's been most successful is removing the fines from the feed and removing the oversize. And that is integral to the process because it also helps in the decapitation process. So everything needs to be screened for the fines and for the oversized, agitated for a significant amount of time to decapitate. And that seems to be the best SOP for now. And it really helps with dust management. We are working on an electrostatic solution to discharge those fines so they're not statically charged and they don't stick to the surfaces, or using static to attach to one surface or another. But I think that that's pretty much under control. And then the other thing is that just the tolerances have to be so tight for the dust not to get everywhere. And so we are looking into different types of gaskets around the crevices in the device. I didn't expect it to be this problematic. And, it's a simple solution of, just what I've seen in other devices, using tape or something like that. I don't like the way tape looks. However, I must say it really is easy to install and easy to clean, but it doesn't look very good. So, we are using different types of just seals that both are easy to install and easy to clean. Sealing the gap is not the issue. It's just that it's a good seal, so it actually helps, but that the maintenance involved is reduced. So if it's just more work, it really is not very helpful to have something that just actually gives you more work, right? Because you have to clean those gaskets. And then the other issue is that because you have higher airflow, you have higher feed rates. Well, now you also have higher throughput, right? And so the plates get full extremely fast. Like the process is too efficient. So we're in the process of identifying the best materials and methods to continuously clean the plates. And this is for a more industrial type application. If we can't do this cost effectively, this would only make sense on larger machines, right? But hopefully we can make it cost effective where the smaller scale models will have a continuous plate cleaning device. And that'll be helpful for everybody. But yes, we're in the process of really identifying I have a whole bunch of ideas and materials that we have to test to see what works best, that it doesn't interfere with the electrostatics, but yeah, some sort of continuous process to clean the plates. Because like I said, the problem now is that as you increase the throughput, the plates just get full very fast. So you have to stop the machine, clean, stop the machine, clean, stop the machine. And that interval of time, even though it's extremely quick, but it could cut your throughput in half if you're stopping the machine so frequently. So that's another thing that we're working on. That'll probably be available for another iteration of the machine, probably the next 1.5 or something like that. The other issue people are having a lot of problems with is the vibrating feeder. The capacity of the vibrating feeder is very small. Adding a bigger hopper is definitely an option. And that's something very simple. So I'm still analyzing if it's worth the expense just to add another hopper or just a different feeding mechanism altogether for smaller labs. I personally think it's fine. But also, we're looking into different materials that are not electrically conductive to prevent friction on the surfaces. So like on the bottom funnel, because it's acrylic, it's electrically conductive and the particles will stick to that very well. It's easy to brush off, but the particles stick. And so in the GMP version that we're doing, you're actually just going to push a button and those surfaces are going to clean themselves through vibration. And then these hoppers can have coatings that also prevent particles from sticking in and just making it easier to clean and more continuous so you don't have to stop. But there's always a balance, right, between manufacturing complexity, product cost, because the idea is to make the machine better and reduce price at the same time. But I mean, we can get crazy and make the machine better and better and better, but then the price is going to be going higher and higher and higher. And I want this to be accessible to as many people as possible, not as least as possible. So there is that. The gap between the funnel, the funnel where the product comes out of the electrodes and into the vibrating feeder, that is also a point where the positive airflow spills out and particles fall. So we need to close that gap, and that's very simple. A skirt of electrically dissipative material, so particles don't stick to it, and you don't have that air exiting through there, taking out those fines with you. But that, again, is greatly mitigated by removing the fines from the system. And that's kind of where we're at now. I think the vibrating feeder works well. We do have another option for a vibrating feeder, like you can use a Wretch or other brands of vibrating feeders, but I mean, they have extremely high price points. So I think from an entry-level perspective, the vibrating feeder that we have is good, but we are now offering the option of an even better vibrating feeder, albeit extremely expensive, but it is what it is. The suction feeder that we're using is great. We just got pharma certification for our hoses. The hoses, the polymer that we make for the hoses that tribocharge the particles are now USP, FDA, and all of that good stuff. So that's fantastic. The plastic parts are all food grade, but now we're adding a coating to make them even a higher rating of food safety. And it's just making them a little bit easier to clean and less accumulation in places like the diffusers and things like that. So that's also an achievement. Mind you, it's not so simple of just saying, let's add a coating to it. Every coating, every surface that you put into the system has an effect on the particle. It'll change the charge or particles will stick to it. So let's just say, oh yeah, let's add a food safe coating. No, you have to test every single coating that you put, how it influences the particle, and take those electrical measurements to see if it's affecting the charge in any way or causing some sort of clumping or something like that. So, you know, it's not so simple of just buying something off the shelf, some adhesive, some coating, because it may or may not work. You know, it's incredible how nuanced the process is. You know, from a layman's perspective, from a user's perspective, it's great that it's elegant in its simplicity, but the physics behind it can be very complex. I have a lot of conversations with engineers that do this sort of stuff for a living, and a lot of the recommendations that I get, you know, I have to be respectful because I already know they don't work, right? But the physics, the science says that they should work, but they don't. And so it's really hard having these conversations with engineers that have been doing this for 30, 40 years and trying to explain to them, no, that's not going to work because I know it doesn't work in practice, right? Theory is one thing. That's fantastic. But in practice, things don't always pan out the way they do. But anyway, that's where we are right now. Stay tuned. Bigger and better things coming. We should have the GMP version out very soon. You'll see some videos. We're partnering up with some top brands in the country that are going to take our stuff for a run. And we continue with the improvement of our products to make them as cost effective as possible, as user friendly as possible, and just make that ROI for you guys as great as possible so your business can be successful, because if you succeed, we succeed. Thanks for watching.
Hi everyone, thanks for watching. If you found this video entertaining and you learned something today, please consider supporting us by clicking this button here. Much appreciated.
What are you doing, pretty lady? What's your name? What brings you to this place? Talk to me. See, guys, this is what I have to put up with every day. Fucking people.